Thank you very much, Diego. Funny, I understood almost everything you said. It's actually terminology is very similar in both languages, so I understood what I was talking about. Okay, so it's very nice to be here. Thank you very much for inviting me. It's my first time in Mexico City. It's actually, I imagine that it's going to be very hot, and here it's actually it's stereotype, like everybody has about Mexico that it's very hot and humid, but actually it's completely opposite. It's much nicer climate than in New York, that's for sure, because in New York it's now very humid and hot, and so here is just amazing weather. So I'm going to talk about this topic that I have been kind of pounding recently with my colleague Kerry Emanuel from MIT. We've been doing this for maybe 8 years now, with various degree of success, and we call it like it's self-organization or self-aggregation. We call it self-aggravation. So because it's really a very difficult topic. So just to give you kind of this background, you of course probably many of you have seen this figure before or similar figures. That's I like to show to my students in my undergraduate atmospheric physics class. Basically that encompasses all our knowledge about climate system in very simple way, and this is just fluxes of energy in the Earth's climate system, and you see that many processes like reflection of sunlight, greenhouse effect, and of course hydrological cycle, all these processes involve clouds. So clouds are extremely important and for understanding how climate system works, and it's very important also to understand how clouds would react to projected climate change. I don't like the term global warming, because that's kind of became certain political accent to it. I think we should say climate change, then people would agree with you more. Okay, so one of the things that motivated this kind of study is this notion or this knowledge that we have from paleoclimate studies. Although it's a little bit controversial, and the way how you collect this kind of evidence can be criticized, and it's still not settled science, it's difficult. But from these very old paleoclimate reconstructions of temperature in the long past, say 50 million years ago, 55 million years ago, when amount of CO2 was very high, extremely high compared to today. It was not twice or 3 times high. It was from 6 to 8 times higher than today. And during those times, of course, planet was very warm. But surprisingly, from paleoclimate reconstructions, the tropics have not been so warm as you would expect from simple just increasing CO2. They've been basically about the same temperature as today, maybe slightly warmer, but not much. While extratropics, polar regions were extremely warm, to the point that crocodiles fossils are still found in Alaska, for example. So and palm trees prints on coal, for example, you can find in a tundra region, with tundra today. So it was very warm climate, but tropics were not that responsive to CO2 forcing. So it was kind of interesting what kind of powerful negative feedback could be working, if of course it's true, because again this reconstruction is not settled yet. But still there are many other things, many other sources of evidence that tropics were not that warm. I mean, well, they were warm, but not that warm that you'd expect from, say, 6 times CO2. So I use more, of course, we can use only models to test some of those ideas. We cannot increase CO2 to this level for a science experiment on a planetary scale. So the only way we can test those ideas is using models. And I use this approach, which is called radiative convective equilibrium, which is very commonly used in cloud resolving modeling community. It's climate model analog for cloud resolving models. And in this framework, you basically run your model freely. You don't specify anything except for maybe you prescribe sea surface temperature and maybe amount of CO2, for example, in the atmosphere. But everything else is kind of bubbling convection. And it's very good approximation for tropics, because tropics export only about 20% of energy to exotropics, and this 80% energy is basically just the exchange of short wave and long wave radiation. Tropics as a whole. So tropics as a whole can be considered this kind of state of atmosphere in radiative convective equilibrium, unlike, say, mid-latitudes where transport is very important. So you compute everything, microphysics, transport by convection, vertical transport. You can add planetary rotation, for example, like Coriolis force, and simulate, say, tropical cyclones. You compute radiation. So everything is, and domain of doubly periodic. So basically, like real Earth, it's periodic. So there are no lateral boundaries. There are only top and bottom boundaries. And you run this model for a long time, and then you compute some statistics from that and responses. So the model that I use is my model, which is called System for Atmospheric Modeling. I developed that model while I was graduate student, and it has, of course, evolved since that time. It's an elastic model, so there are no sound waves. It can be two-dimensional, three-dimensional. It have all these different microphysical packages, and it's massively parallel, so it can be run on very big computers using many processors. And currently, it's pretty popular in the US among cloud resolving modelers. At least I know that currently there are about maybe 20-30 active users of that model, and more than 100 people downloaded it at various times. You can download it too, just sending me email, and you can get one. So this is how typical radiative convective equilibrium simulation looks like. So you have this bubbling convection. This is domain of size 512 kilometers, and the resolution grid spacing is 1 kilometer. And you see that it's a convection just happily bubbling. There's nothing really particularly interesting is going on. So now if you increase domain size, something, or reduce resolution, which is kind of weird, make it more viscous flow, you kind of get this kind of interesting result that instead of this happily bubbling, convection aggregates into this one spot surrounded by a very dry region. It's called, this phenomenon is called self-aggregation, and there have been quite a few papers currently written on explaining this phenomenon. And what is interesting about it is that if you compare this disaggregated state or this happily bubbling state, say you take initial 5 days or so of simulation when it's not aggregated yet and compare it to aggregated state, and you look, say, at outgoing long wave radiation fields like shown here. So if you look at mean, you see that in disaggregated state, or this bubbling state, there is much less long wave radiation leaving the area to space than in aggregated state. So aggregated states basically open the skies, and all this surface temperature, or in this case sea surface temperature, has a chance to cool because of that. So there is this negative feedback, positive due to aggregation. So aggregated state makes atmosphere drier, reduces greenhouse effect. As a result, you increase outgoing long wave radiation because water vapor is major greenhouse gas. So that's what aggregation does. Another piece of puzzle that we get accidentally when I tried to change surface temperature in wide range, and then I accidentally found that this phenomenon of aggregation into this blob of convection happens only at certain temperature and above. So there is a threshold between for sea surface temperature between a state of when convection aggregates and state when it doesn't. You can see this kind of two set of plots for different temperatures, and in this case, particular case, aggregation happens about 297 degrees, which is basically current average temperature of tropical sea surface temperature. So, and again, if you compare these aggregated states, which are blue here blue states are disaggregated, states, so cold states, and warm states, and what is shown here is relative humidity, horizontal axis relative humidity, vertical is height. You can see that aggregated states have smaller relative humidity, so atmosphere is drier than disaggregated state. And now there have been several observational studies of this phenomenon, particularly a study by Tobin et al., who's shown on the right. Here it's the same plot, but found from observations looking at some soundings from some sensor that actually looks at vertical profiles of water vapor. And you see that they looked at certain areas, say 10 by 10 degrees in size, so about 1,000 by 1,000 kilometers. And when they saw many convective clusters in that region, they would call it disaggregated state, so it's not aggregated state. When they saw one big or two big clusters, that's aggregated state. So they classified by that, and then they plotted relative humidity in those states. And they see the same thing that when convection is more aggregated on real Earth, it's actually drier. Atmosphere becomes drier around that convection. So that's actually confirmed observationally, this behavior. So why convection actually aggregates in a certain temperature and doesn't in other temperature? There are a couple, at least, or two or three mechanisms proposed over the years. The one that I kind of like is recently was published by Kerry Manuel and et al. Back in 2014 in James, I think. So basically, what is shown here is a running single column model, very simple one. It's also in a radiative convective equilibrium. Single column model is basically climate model's physical column, just one column, that not forced by any advection, just basically again allowed to run convective schema or so. So they produce this kind of equilibrium state. It's at different temperatures, and then they remember this aggregation creates these dry regions, very fast areas. And if you look, actually, I didn't actually mention that. If you look at this, you see that first what it starts, this blue big thing, it's dry regions, they grow. It's not that the convection actually aggregates, it's basically pushed in the region by these dry regions around it, pushed it into region. So it starts from drying, and this drying seems to be unstable process. So there is some unstable process that enforces this dry region. So initially you create some dry regions by chance, like say by outflow from convection somewhere, this dry region, and then somehow it becomes amplified. And this amplification is called radiative convective instability, and it was pioneered by Kerry Manuel explaining it. So basically what you do here, so they have these profiles, and then what they did, they reduced uniformly water vapor by 20% everywhere at all heights. So basically just saying, okay, what is the response of radiation to that in one time step? So they reduce it by 20% and then compute radiative heating again. And this is what's shown. Red lines are a response of solar radiation. In this case, it's not particularly important. But more important is response of long-wave radiation, which is blue lines, and the red ones is a control simulation. So now you see that for left one is for temperatures 25 degrees Celsius, that's sea surface temperature, so it's cold SST, and the right panel is for warm, very warm SST of 40 degrees Celsius. And you can see right away that basically you see that in this stable case, or this disaggregated state, you see that net response of radiation is warming. So you reduce water vapor and you're warming. How it happens? Well, when you have not a relatively small amount of water vapor in the atmosphere, it's a greenhouse effect. But it's not saturated. The effect is not saturated. So if you reduce water vapor amount, you basically reduce emitters of long-wave radiation, number of them, and then it's basically it would cool less. It would provide less greenhouse effect. Less cooling means it's like warming. Less cooling is the same thing as warming, relative to control. And that way, if you have this subsiding cool air or dry air, in that case it's actually warming. And in that case, it's positive negative feedback, it will stop because it's becoming stable. So in this case, it doesn't really work. And so that's why disaggregated state does not aggregation does not happen at cold temperatures. But when you have warm enough atmosphere, you have a lot of water vapor, and in low levels it becomes saturated in respect to radiation. So if you even reduce slightly the amount of water vapor, it doesn't affect low troposphere at all, because it's already saturated, but it affects strongly, of course, upper troposphere. So this radiation emitted by low levels goes now through that troposphere, which does not have enough water vapor now to stop it, and that way you actually cool low troposphere. And so the slide below shows the net effect for all temperatures, so that if you increase it from 25 degrees to 40, so you go from here, when there is net warming effect, which is negative feedback, to cooling. So when you cool then subsiding air, you cool it, it's actually subsiding even more. So it's certain temperature, there is a switch from that regime to a different regime. So at certain sea surface temperature, you develop this convective instability. So that's basically the mechanism. So that allowed us with Kerry to propose this kind of, sorry for a little bit, not very, this mechanism that we call self-organized criticality. So we believe that tropical climate, because of this effect, is like a glass of water with ice. So you all know if you add some heat to that glass with ice, temperature will not change, right? Some ice will melt and that's it. So, and if you remove some heat from a glass, it also will not change temperature. So you see that this is kind of phase transition. So we believe that because of this effect with atmosphere, with this aggregation, self-aggregation, tropical atmosphere can be in this state when in between these two states, disaggregated and aggregated state, so basically liquid water and ice. And so basically you warm SSTs, let's say by putting more CO2, that will cause more aggregation because it's warmer SST more conducive to aggregation, to this effect. And that would dry the troposphere, as we saw. And drying troposphere actually would reduce greenhouse effect and try to cool SST back. Of course, and then that would cause less aggregation or disaggregation of convection, and that would remoisten again the troposphere. So there is this negative feedback that keeps tropics at about constant temperature. Of course, it's very difficult to prove because for that we need to put really, like say, double, triple CO2 and see what happens. We cannot do it in actual tropics, although we're doing it right now. So eventually we will know the result, maybe in, I don't know, 20, 30 years. So I cross my fingers, like I keep my fingers crossed to live to that time and to see if it was right. But of course, we have models to test some of it. So in this case, we use this approach. We need really big domain for that. The thing is, this mechanism, this radiative convective equilibrium, it can be shown mathematically that it works the best for big scales. It doesn't really work well for small scales. One of the reasons is that for small scale you always have wind shear and other things that smear this initial moist, dry thing. The simulation that I showed you before didn't have mean wind. That's why it kind of was easy to aggregate. But if you have actual atmosphere, you have this winds everywhere, all these waves, disturbances, that kind of tend to smear all these initial dry patches. And that's why on small scales it shouldn't work. But it should work on very large scales, say on Kelvin wave scales, Madden-Julian oscillation scales, kind of very large disturbances of very large scale. So the bigger the scale, the easier this mechanism works. So you need really a large domain to see anything. So what I try to do here is just to run the same convective radiative convective equilibrium simulation, but using a really large domain. In this case, it's a half of Earth's circumference, so it's 184 degrees equivalent in longitude, so it's about half the Earth, and it's going to 46 degrees north and 46 degrees south, so it's about half of extent. And the reason I didn't go farther, because this model, this version had Cartesian grid, and it would be very awkward to go further, because, you know, in the actuality is getting smaller and smaller space on actual Earth. So this is kind of some compromise. And what was specified here is sea surface temperature. Yeah, sorry. What the? Oh. So that's just a visualization. And we specified sea surface temperature, which is kind of similar to observed kind of mean sine-like profile. So it's warm in tropics and kind of cool off towards mid-latitudes. And so there is some baroclinicity, which you can see that you have extratropical cyclones as well. And in the middle you have this kind of tropical ITCZ with some, you can see this big waves, Kelvin, look like Kelvin waves moving to the east, and some smaller scale waves moving to the west. And so all sort of kind of things going on here at once. Of course, there is no MGO here because the domain is too small for that. So how you now look at all this kind of, it looks like a very busy picture. So what we try to do here is to basically use the same methodology that was used by Tobin et al. Study that I mentioned before, the satellite study that they showed that actually relative humidity indeed is reducing at aggregated when aggregated convection is present. So we use the methodology. So we take, I have many, say, over a period of more than a month, snapshots every 3 hours or so of these three-dimensional cloud fields and other fields. So you have this cloud cover, let's say, but cloud cover is kind of not very easy to work with because small clouds, shallow clouds, deep clouds, all look the same on a visible kind of image like that. So I'm interested in these deep clouds, and deep clouds, of course, you need to look at temperature of tops to say that they're deep. So we use brightness temperature, the same as a study by Tobin et al. Brightness temperature, so it's basically infrared temperature. And now you can see where deep clouds are better. And now you reduce it to, so you take this scene like that and you average it to 50 kilometer boxes, because satellite resolution was 50 kilometer in that study, so to be kind of consistent. And that way you actually make clusters more visible, because you kind of, that way they tend to be two kind of continuous kind of picture, which is difficult to see individual clusters. So you have clusters like that, middle plot here. Now you count them. basically you write very simple algorithm, which is like 10 lines of code, which is called spillover algorithm, something. It's very simple algorithm, and then you fill all the clusters that are not interconnected with different numbers, and then you count them, and at the same time you count area of clusters. So it's very easy to do. So this is what shown, different colors just show different clusters. So now you see that you have really various clusters of various sizes. And you do that for each scene that you have. In this case, it's like more than 300 cloud scenes, like that. And you do it only for tropics, so for this tropical belt. So, and then you plot PDF. And then you do the same simulation, but you increase temperature by 4 Kelvin, sea surface temperature uniformly everywhere. Just make it like warmer world. Now you can see something. Okay, let's see. This left figure is a PDF, so number of clusters on the vertical axis, and horizontal axis is clusters area in square pixels. So you see that distribution is power law, right? For most of the clusters, except for very big ones. Those so-called superclusters, those that are really Kelvin waves and Rossby gravity, equatorially trapped Rossby waves. So that's very, very, very big clusters. And you see that now, now if you look at the warmer case, when you plus 4K, which is red, you see that, as I mentioned before, smaller clusters don't care about this instability. You see that smaller clusters are all the same. PDF looks exactly the same. But big clusters, now the number increases by a factor of 10. So indeed, at warmer climate, very big clusters, their number increased dramatically. So climate system is trying to produce more aggregated convection on large scales in this simulation. In terms of power law, it is indeed observed in nature. This right figure is from observational study by Peters and al. Who look at satellite data, and is basically similar plot, PDF, and area in square kilometers, not in this kind of logarithmic scale. It doesn't really matter. Which is so you see that it's indeed a line. So it's power law, except for very big clusters. So very big clusters don't obey it, like in simulation. So climate system may be indeed in this state on between clustered and unclustered convection. That's why this number of superclusters kept kind of low. Because if you increase the dry atmosphere, it's immediately kind of negative feedback that gets rid of them. But if you don't have this feedback by increasing by 4 Kelvin, I remove this feedback, right? I just increase everywhere temperature. The number of clusters dramatically, superclusters dramatically increases, which actually would, if I let SST evolve, and I haven't done that experiment yet, but I will do that, if you make it interactive sea surface temperature, it would cool it back. But that remains to be seen. That remains to be done. So now, if you look at statistics, similar statistics that Tobin and et al. Have done. So what we looked at these 10 by 10 degree areas, or those cluster regions, 10 by 10 degree regions, and we just count those clusters in a particular region. Say, if we have, say, this on the left, it's like 6. This one is less aggregated state because you have many, and then when you have like 1 in this case, that's aggregated state. That counts like aggregated state. So we basically, this is our metric. Of course, it's not perfect, but statistically, if you have many clusters like that, you can eventually say that if you have really few clusters, they tend to be aggregated, and if you have many clusters, that's disaggregated convection. So now let's look compared to observation. So left one is a model. Horizontal axis is number of clusters. So the smaller the number, the more aggregated convection in that particular box. And vertical axis is precipitable water or water integrated water vapor, so the amount of water vapor in atmosphere. And the right is a similar kind of plot, but from observations for today's atmosphere. And you see that indeed, in observations, you see this, that when a convection becomes more aggregated, it's significantly less water vapor in that box. And the same thing can be seen in the model, the same response. Now, if you look at radiation, so left one is incoming solar radiation. So you see this interesting phenomenon that aggregated convection has less incoming solar radiation, which is kind of nonsense, right? How incoming radiation depends on how many clusters you have. And the thing is, it's just because it's more nocturnal in nature. So when you have superclusters or more clustering convection, it appears that it's actually more night conditions than day conditions. So that's why incoming radiation, and that actually has very strong effect, because without this effect, there would be wash. So that basically the effect of short wave and long wave radiation would cancel out due to aggregation. And that would actually, in another study by, I think it also was Tobin et al., they actually shown that there is no effect of aggregated convection on net radiation absorbed by the climate system. And the problem is because they looked not at the absorbed solar radiation, they looked at reflected solar radiation, which is not the same thing. It's the same thing for climate model average over 1 day. But if you average over, say, 1 hour, it depends if it's night or if it's day. So basically, absorbed solar radiation is not the same as reflected solar radiation, just changing sign, because your incoming solar radiation is also different. And so if you take that effect into account, then, yeah, this is net. The right is a net. That's what heats the climate system. So it's absorbed solar radiation minus outgoing solar radiation, outgoing long wave radiation. So that's net. And you see that aggregated convection is about 150 watts per meter square produces this outgoing net effect, cooling effect, than disaggregated convection. 150 watts. That's doubling CO2 is only 4 watts per meter square. This one is 150, so it's such a powerful effect. So that's why I think so far we're kind of optimistic about our hypothesis, but we need, of course, more to show it in interactive framework when you have actually feedback to sea surface temperature and see how the whole thing actually works. That's in near future, so stay tuned. And that's just some intermediate summary on this part. So distribution of area clusters is described by Power law, which is itself is not really explained yet why it should be the case. But the response to warming of surface or climate system in this idealized climate system is really only felt by only manifests itself only by superclusters, but not small and middle-sized clusters, because middle-sized clusters, they're not so responsive to this radiative convective instability mechanism, again, for the reasons because there is too much noise on those scales, I think. That's why they're not responding. While bigger clusters, they basically, they have more time, so to speak, for radiation to work. And that's why they're more responsive. And so the overall conclusion that so far these idealized simulations support our hypothesis that in warmer climate or increasing CO2 can lead to more aggregated tropical convection in the form of superclusters that would have powerful negative feedback. But it's only in tropics. In high latitudes, It's not the case, unfortunately. So we live not quite in tropics. In the interest of time, I skip this thing because that's really too technical, I think. It's just similar thing, but about MGO. And I will show some preliminary results that, remember that I showed this picture. And main thing that, we have been criticized for that too, that we put walls, because this domain is rectangular, we put walls in the north and south. I haven't mentioned that, but you have to. Why not periodical? Because cyclones in northern hemisphere, if they get to the southern hemisphere through periodical domains, they become anticyclones, and that's not good for simulation. So that would be really bizarre. So to avoid that, we just put walls. But of course, wouldn't be nice to go to the poles all the way, or almost all the way. So take into account this the reduction in area with latitude. So for that, you need to go to latitude-longitude grid. And if you do that, you build right away from existing model with relatively small effort, because you don't start from scratch. You go to global cloud resolving model. So what I'm going to show next is some preliminary results on global cloud resolving model. So basically, it's just equations. You see those. I don't want you to see them. It's just governing equations, but those that underscored by red, those terms you need to add to latitude-longitude grid. That's all. So just very few modified terms, and you're done. And also because there is pole problem. In latitude-longitude grid, you all know, velocities are not defined at the pole. And there are other things, like delta x goes to 0 and delta y goes to 0 there. Certain terms become infinity. So singularity point. So there are ways to avoid that, but they involved pretty elaborate methods and significant change of the code structure because of message passing on parallel computers, how it works. To avoid that, I just put a big building on the pole. Why put a skyscraper there? You think that like one of those Dubai kind of type, no? Like whole troposphere, even higher than Dubai, and a little bit wider than Dubai, say 1 degree in the radius. So it's about 100 kilometer kind of radius building. That seems to be kind of big, but actually, if you think about how big the Earth is, you think that putting building on the pole would do much harm to, say, tropical simulations that I'm mostly interested? Probably not. So for now, it's a kind of temporary fix. I'm not insisting that this is everybody should do that, but that's allowed it to do it fast. So this model uses 16 land types, which I was fortunate enough, another student graduated right before this exercise, and she actually built a so-called simple land surface model, simplified land model, and so it was already available to me. I added just different land types, a little bit some coefficients here and there, but it was easy to do. And it has realistic topography with 4 kilometer grid spacing. So, and topography is implemented so that I wouldn't change the code, because remember I have Cartesian grid. I just put so-called block topography. You see these certain cells are just filled with stuff that causing velocity to be 0 there. That's basically what topography is like. Air just cannot go through it. And it works surprisingly well. It's called immersed boundary method, or variant of it. So this is simulation, a 4 kilometer simulation of about 40 days. The resolution of this simulation is actually such that 1 pixel, I believe it's like high definition here, is about what? Is about 8 grid points in 1 pixel of this image. So you don't see actual resolution here. It's impossible. And it runs relatively fast. It takes about it runs 6 times faster real time, which is still kind of relatively slow, but it's 4 kilometer grid spacing. This simulation, 40 days, takes about almost 1 million core hours on supercomputer. So it's really a little bit expensive to run. Yeah. You need to have large account. And so it cannot be done on a Linux cluster. So just another thing, just another view of the same simulation, just looking at the Earth, and a little bit turned it to show this building there. You see the place where building is. And if you look carefully, well, especially in the bottom, do you really see anything artificial? I don't know. Maybe, but who cares, right? It's Antarctica. For northern latitude, of course, it's important. Some waves can be. But even here, you see this wave coming around. I don't know. But it's very nice fix because putting this pole point, it could be done, but it would change the code dramatically and would take considerable time to implement. So this is just some comparison to reanalysis of this simulation. Like top is model, bottom is European Center reanalysis for the same period. This one is monthly precipitation, so it's total accumulated precipitation for or mean actually divided by 40 days or so. So you see that the general structure very well captured. You see, of course, it cannot be one-to-one. It's not weather forecasting problem. This one is basically free run. But I'm glad that this is basically one of the first runs, and without really much of a debugging or tuning, I was able to capture main features of general circulation in this respect. This one is water vapor, column water vapor. You can see that it's also well captured at this position of fronts, with dry fronts and so on. And this one is, I looked at probability or Daniel cycle of precipitation. Horizontal axis is 24 hours. Vertical is precipitation rate above 1 millimeter per day. So you see that it for various regions, say for example for Amazonia, you see that it's about like maybe 3 o'clock maximum, 2 or 3 o'clock, which is observed. So overall, even 4 kilometer grid, even though it's relatively coarse, it's still coarse. Of course, to resolve nice convection, you need probably 1 kilometer grid. But still, even with such relatively coarse resolution, you're able to reproduce the annual cycle of precipitation. So it's dated tsunami, 3 billion grid points, blah, 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 how to save for this and write, that's made challenge, of course. It's now, of course, this model is very expensive to run. So you need very good application for it. One application that I mentioned before is this kind of cluster analysis. That's, I haven't done it yet, but another one is forecasting, weather forecasting, right? So you have this thing, why not forecast some tropical cyclones with that? It's relatively cheap because you run only for a few days. You don't need to run for months and so on. So my first forecast was 3-day forecast of Hurricane Katrina. And this is about at the end of simulation. You see that indeed it looks like Katrina. Let me zoom in. And it's actually hit exactly New Orleans in this simulation. So it was very successful in this respect forecast. But it's only 3-day. So next I turned to Hurricane Irma, which was last year hurricane. Maybe some of you remember that hit Florida. Of the United States, and the difficulty with this hurricane forecast that in this case it's about 10 days before it's actually hit, or maybe 8, 9, something like that. But it's a forecast for September 5 from various models, various forecasting models. You see that it's all over the place. The actual path is, of course, it was west coast of Florida. It was just brushing it. And only few models were able to predict that. One of them was a European Center model, but most other models were completely all over the case, all over the place. So it was very challenging forecast. So I tried my model. I initialized on September 5. So, and I used 10 ensemble members from European Center. So initial conditions were from European Center. Maybe it's a little bit easy. I should have used NSEP. So it's not very patriotic. And then it's everybody knows that initial conditions from European Center are easy. The problem is if you do actual forecast, you won't get them. That's the problem. You can get NSEP, but you cannot get European Center in real time. But I tried like the best. Let's kind of not distract, like, let's say that it's the best initial conditions that are out there. And what can we do? And European Center also provides 10-member ensemble initial conditions. So very convenient. So I used 10 members. But of course, it's pretty expensive still. So I used for track forecast, I use 17-kilometer model, which is the same model, just degraded by factor of 4 and considerably faster to run it, 50 times faster than real time. So it still can be used like forecasting model, 50 times faster. And then I run one deterministic run forecast for intensity forecast, because you need really high resolution for correct forecasting of intensity of tropical cyclones. And now here shown some results. So red lines are ensembles, and black line is the actual track, and green one is ensemble mean, which actually puts the projected track on the west coast as it should. And deterministic forecast kind of also, but a little bit less accurate, but it's also going to the east coast. The track is not perfect. It's a little bit north from Cuba than it should be. But overall, I was very pleased with this. So now I found actually one member out of those. That was very good. So basically reproduced the observed track. So, but the problem is, of course, intensity. So here, a left figure on the top is showing the intensity, the center pressure, the lowest pressure in the center of tropical cyclone. Green are ensembles, is 10 members, 17 kilometer grid spacing, and dot is observed, and the blue line is a 4 kilometer forecast. So you see that how it's sensitive to resolution. So basically 4 kilometer kind of reproduces a low pressure. The bottom is actually IFS, or European Center model, which has actually difficulty doing so, even at high resolution, because they use hydrostatic model. So high resolution doesn't really help much for them. Here on the right is the intensity forecast. So dots again, it's observed. Green ones are a 17 kilometer grid, and you see that IFS also has similar 80 kilometer per second intensity, which is largely underestimate the actual intensity, or wind speed. And you see that high resolution helps and reproduces the observed intensity. So I'm very optimistic about that. Unfortunately, I don't have much computer time to continue this kind of exercises. So far, I haven't found much interest from certain agencies. I think it's some kind of circle of people there, kind of defending themselves. I didn't say that. Okay. So this one is just visualization of that deterministic forecast, just for you to see from the model. So it starts and then it goes. And it starts from very coarse grid. It's like 30 kilometer grid spacing. And it still recurs, so it's going. So now it's maximum intensity. And now it will turn north, very sharp turn. And it brushes on that Florida. Okay, looks pretty realistic, I think. So future plans with this model. And of course, it's very suitable for extreme weather events. I haven't shown here, I tried high resolution forecast of Long Island weather. And I was successful to predict some line of thunderstorms that was completely under-predicted, and it caused considerable flooding on Long Island, and forecast said clear skies, sunlight, sunshine whole day. And but you need very high resolution for that, and then you're able to reproduce it. I haven't shown it, but those who are interested, I could show later. And the next thing is, of course, I need the global ocean model with that thing. The funny thing about global ocean model, first of all, dynamical core is the same as atmospheric model, just slightly different buoyancy term because of and also there are no clouds. That's so nice. And also the time step is very large for ocean, because ocean moving is very slowly, and because it's an elastic model, there are no sound waves. So I don't care about those. So ocean model, my projection is it would be 10 times cheaper to run than atmosphere model for the same grid. So it would be basically come for free. It would take only about maybe 5-10% of computer time. And then I could run maybe interaction of hurricanes with ocean and so on. Okay, that's it. Gracias.
Tenemos el micrófono.
Thank you very much, Professor Marat. So this brings back memories of when I went to talk to Professor Marat, and he would talk about some of these things, and I didn't understand one word he was saying. Now I understand some of it. So I won't trust you if you don't have any questions. No les voy a creer si no tienen preguntas, ¿eh? Y eso que se saltó la parte difícil y técnica, así que. ¿Entonces, alguna pregunta? Some questions? ¿Preguntas? Hey,
thank you, Martin. I followed your work for a long time.
Thank you.
And enjoyed the talk. I had a question. You mentioned self-organized criticality, and you put it in terms of sea surface temperature, and I think it was the manual. Mm-hmm. And I was thinking more the kind of traditional, so to speak, in terms of column water vapor, kind of the Nealon, Peters, all that kind of work. One question: have you tried to replicate their idea of self-organized criticality in terms of column water vapor with your runs? Just
like
do you get the same
plots?
Exactly. Do you get their plots?
We have looked. Other models have looked, and we don't see it.
Okay.
It goes
straight. The variance goes straight up.
Yes. Some people believe that it's because of saturation of a radiometer that does this.
Right. Okay. Also, I was going to relate to that.
All models like some fundamental physics.
We measured it with GPS precipitable water vapor in the Amazon, and what we were doing with David and one of his students, Kathleen Skiro, I don't know if you know her, and what we looked at for land was that you have kind of the critical behavior, but you don't have the self-organized criticality. You get this continual increase in the variance. It doesn't,
Yeah, that's what I.
So, because everything you've done so far, you've done it over the ocean. So the idea would be that there may be some different type of behavior, land versus ocean.
Yeah, but I think ocean, one of the things, first of all, ocean is 70% of territory. Right. In tropics, even probably more. But, and second of all, over the land, I think there is so much noise produced by all this terrain topography, non-uniform heating, that it's more probably an effect of moisture feedback kind of thing. So moist patches create more aggregation. So it's not radiatively driven. More, it's some different mechanism which also operates. I haven't talked about that, but of course that mechanism is also can be important.
Thanks very much. Very nice talk. I was wondering if you were to replace your convective scheme, resolving scheme for clouds by with Cambridge type of thing. Would you see the same kind of behavior? I mean, would you go into more aggregation than disaggregation?
You mean in terms of clusters?
Yeah.
I don't know. Maybe it should be tried, yes.
Oh, it's just because it would be interesting to look into what global models using those kind of things.
Yeah, but global models, they have very maybe 50-kilometer grid spacing, kind of typical. So they should look at that. Yes.
You could run WRF, for instance, with that type of thing. Design this type of experiments with Cambridge and convectivity.
Yeah, that would be interesting.
Yeah, all right.
¿Alguien más? Well, I have a question. So at the end, you talked about hurricanes and first the aggregation of convection. And so what role do hurricanes play in this view of the tropics and deep convection as a thermostat for this forcing due to CO2 or whatever?
Well, they're of course important. That's what people generally care about. We have done some study back several years ago with Kerry about this radiative convective equilibrium with rotation, where we looked at this response of hurricanes to warming of sea surface temperature. We didn't see this criticality there, so this kind of switch on-off, because that in that system actually organization is very influenced by Coriolis, kind of by Rossby radius, and we saw that in warmer climates hurricanes become bigger but less frequent, and that's basically many other studies, recent studies. But in terms of effect on climate, except for this kind of brute force effect that hurricanes bring with them, in terms of statistics, I think they're not that important, because even today they produce only about 5% of precipitation in tropics, and in terms of cloud radiative effect, they're very unimportant. But they may be important for stirring the ocean, kind of mixing the ocean. I don't know. That's probably why it's very interesting would be to have coupled model like that with hurricanes to see some of those effects. Yeah, maybe they're important. But my first instinct tells me that they're not. I mean, in terms of radiative budget.
That makes sense. ¿Alguien más? ¿Alguna otra pregunta? Huh? So I have one more question. So then, thinking about using your model for forecasting, it seems to make sense to talk to other people, because you're running these very expensive simulations, but you're keeping your high resolution for, who knows, maybe you get, while you have a risk of hurricane making landfall in the eastern coast of the US, maybe also India, Bangladesh, some region over there, you have a cyclone, and also Japan. So it sounds like something that doesn't make, maybe it's too expensive in some cases, but if you get a more of a global product with multi-institutions, maybe that makes sense, right? Because you resolve all the globe.
Yeah, probably. So far my attempts to reach that community was not successful, because they say that I don't have publications on that subject. So,
then
probably I need to first publish some results, and that will be more inclusive.
Okay. There's a question on Facebook.
All right. Facebook.
Are hurricanes a self-organization response of the atmosphere to the energy increase?
I think I answered a little bit. That yes, they become more powerful because of that, but they become less frequent. And the interesting thing about it that their number in our study, we actually show that theoretically, and also in ideal simulation, kind of confirming this behavior, number of hurricanes is inversely proportional to square root of saturation vapor pressure at sea surface temperature. And it actually can be shown theoretically. And read that paper, it's Khairoutdinov, Emmanuel 2013 in James, if you're interested.
Is that like a scaling argument, or?
Well, it's scaling and also some, it's not just scaling, no, it's actually kind of derived.
No.
Kerry is good in that, deriving those things.
Okay. So no more questions, not even in Facebook? Okay, well, thank you very much, Professor Marat. It was a pleasure having you here.